In today's entertainment news, we bring you an almost engagement story. Producer E. Fields popped the question over the weekend to long-term girlfriend, singer-songwriter Emerald Ruby. Unfortunately, Ruby declined, stating the stone was missing the flaws that make it beautiful. In response, Mr. Fields was overhead explaining that the rare, colorless sapphire can only be for the woman he loves, who lacks all impurities. Here to clear things up, Crystal Violet, a chemist who says crystal field theory is the reason these two lack the chemistry to take their pairing to another level.
Thank you for having me. We'll try to explain or simplify crystal field theory as best as possible as it relates to gemstones. The best known cause of color is derived from a transition metal compound that involves a metal cation, which is positively charged, with unpaired electrons in the d orbital. The vibrant colors we see are due to energy changes when the metal cations and its ligands come together and absorb light, as can be seen here. Let's use Miss Emerald Ruby herself as an example. Think of her as an octahedral chromium-3 ligand cation with 3 unpaired electrons in her d orbital. When she performs, she replaces 1% of aluminum ions and bonds with oxygen to form a beautiful, bright, ruby red gemstone, much like this. The stone emits a red color because it's absorbing green on the color spectrum, which is at about 510 nanometers. This indicates a really large energy change. However, in her daily life, she goes by Emerald and is at a much lower state of energy. An emerald is made up of a similar composition to a ruby with the addition of beryllium as one of its ligands, which changes the energy level and in turn the color of the stone. The emerald emits a green color while absorbing red, which is at about 650 nanometers in wavelength, and that's a much smaller energy change. The colorless sapphire Mr. Fields presented to Emerald Ruby is not unlike either stone. Let's compare it with the beryl gem, which is often called goshenite. It really is an emerald lacking impurities. In other words, it has no unpaired electrons. Therefore, an energy change is quite impossible, making it colorless. While Mr. Fields may have thought he was paying Emerald Ruby a compliment, it sounds like she took it as him saying that she lacked the excitement, the energy as a performer, which reminds me of one final thought. When you're shifting from the ruby over to the emerald, it shows a weakening of a ligand field. Miss Ruby could have thought that their relationship just didn't have the attraction it needed to keep their romance alive. So we know that everyone at home isn't a chemist, so I've brought along my intern to explain things and hopefully simplify it for you at home.
And we're back here with Ethel Orange.
Hi everybody at home, thank you for having me. I'm really excited to be here to tell everybody about the ins and outs of crystal field theory. Alright, so let's get into the nitty gritty of what is happening whenever you're dealing with a different type of complex, the geometry behind it, and where you're going from there. So a lot of it depends on how many ligands you're dealing with that's surrounding the metal, as well as how many electrons are in those d orbitals and how they're being distributed. Not only that, once you know the number of the ligands, you have different possibilities of the geometry. If you have 6, you're going to deal with an octahedral. If you have 10 electrons in your d orbital, you're going to get a tetrahedral shape. However, if you have 8 electrons in your d orbital, you're going to have a square planar shape. Now, the way that you can figure out how many electrons you're dealing with is whenever you're looking at the holy periodic table. You can actually easily count how many electrons by scrolling over from this side over and counting. So let's say we're looking at nickel, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 electrons, and that's going to give us a tetrahedral shape. However, if it had, for example, a positive charge, then in that case, you would go back. Let's say we're dealing with nickel +3. You're going to go back 3 spaces to get that number of electrons that you're dealing with. Now we're dealing with an octahedral, and normally the way that you see is it's in its degenerate state. And what that means is there's not any more energy in one spot or another. They're all at equal levels of energy. However, when the ligands start to approach, you're actually going to see different types of repulsion occur in these d orbitals. Now, those in between the axis aren't going to have that much repulsion with the electrons, but those on the axis are. And that repulsion is actually going to do an increase in energy. So you'll actually see these orbitals split, and there will actually be a level of space in between them depending on how much energy is being generated. Now, what's going to tell us how much energy is being generated? Now, what's going to do that is the different type of ligand that you're dealing with. If you're dealing with a weak field ligand, you're actually going to have a smaller energy field. So the d orbitals are actually going to be closer together. However, if you have a strong field ligand, you're going to have more of a space between them. Now, this is important because electrons at this higher field are going to be able to generate more energy, and they're going to be able to absorb different wavelengths that are going to appear in different light. So they're also going to have different types of spin, and that is in regards to the electrons that you're dealing with and how they're going to be distributed between these different fields. So we're going to get into that, and I'm going to show you different examples of how that affects our octahedral and also the results on color. So more on that in a second. So here are 3 examples that we're going to discuss, and I will help demonstrate for you how these electrons are going to fill the shells. So here we have hexa-aqua zinc 2, and it has 10 electrons. If we go over to the periodic table, we're going to move it back 2 spaces, and just like we previously discussed, we already know that nickel has 10 electrons, and that's where this compound is lying. Now that means that it is degenerate. There's no splitting of those orbitals at all, so we can actually go right in and fill these shells with these electrons. And what this means is it's colorless because there are no unpaired electrons. And in order for us to have color, you need to have unpaired electrons. And depending on where those electrons are lying within those d orbitals are going to help tell us what kind of color we're going to get based on the color that it's going to absorb. Now we have hexa-aqua cobalt, and this has, if we look over here to our scale of our ligands, aqua is actually a weak field ligand. So we're going to have that smaller energy. Now, what that means is because they're close together, it's going to be very easy for these electrons to hop up and remain unpaired. The electrons are going to kind of repel each other. They don't want to share their space with any other electron. So we've got 6 electrons here. Let's go ahead and fill these shells. Generally, with these weak field ligands with that smaller energy, it's going to be referred to as high spin. Now, the way to think of it is all these electrons are evenly distributed, so the weight is evenly distributed, allowing for everything to have more freer movement. May not be 100% technical, but it's an easy concept to grasp on when you're thinking about spin. Now, whenever we move over to hexacarbonyl cobalt 2+, what we're dealing with is we have 7 electrons. Now, if we go over here, we're actually dealing with a strong field ligand. So now we've got a large energy field that we're dealing with, or excuse me, a large distribution of energy in between these d orbitals. So what that means is it's actually, even though those electrons don't want to be next to each other, it costs it more energy to put it up on that higher shelf. So the way that we're going to fill it is this. We've got 7, and we have one lone one that's made its way up there. And generally with a compound that's like this, it's going to absorb violet light, and with one that's on the weaker side, it's going to absorb red light. So you would actually see the reverse of that color. When it's absorbing red, you're going to get green, and when it's absorbing violet, you're going to see yellow. All right, everybody, so I've given you the knowledge and the power and the basics on crystal field theory.